hot tubs and rusty nails. What is the deal? Why did I bring that up? Okay, well, there are uncountable number of chemical reactions on this planet and off this planet in the universe that undergo what we call redox reactions. And these are just two examples. So when you have a hot tub, it is very important that you don't let it get gross, right? You want to clean it and all that kind of stuff. Like if you have any kind of body of water that's small and contained, and whether that's a bathtub or it's a swimming pool or it's a hot tub or something, you need to make sure that like stuff doesn't grow, like bad stuff and bacteria or whatever. Now, in nature, it all takes care of itself, and there are some parts of lakes that maybe you don't want to swim in and all that, but I'm talking about like places that are more like smaller. Like you're not going to reuse a hot tub or a bathtub water over and over and over 20 times without doing something to it. Okay, so we need to kill the bacteria, and the way we kill the bacteria is with redox chemistry, with movement of electrons, with oxidizing. Okay, all of these things, and we'll talk about what they are if you don't know what they are, but all of them pertain to killing bacteria. It's the same thing with if you have bleach in a bottle and you squirt it on a surface and you want to kill the bacteria, it's the same idea as the things that you add into a swimming pool or a hot tub or something like that. It's all redox chemistry, right? Okay, all right, and then we have rusty nails. That is also, if we start out with a piece of metal, and so perhaps this is a nail that is pure metal, and let's say it's iron, made out of iron, old school, like nowadays they're all stainless steel, but let's say it's when, back in the day when things were just made out of iron. And if you leave it outside for too long, what happens? It begins to rust. All right, so then you get that orange color on the outside that is no longer pure iron anymore. That is now iron oxide. And that is also a redox reaction. All right. So let's talk a little bit about what those two things are, what we're talking about. Okay, redox. This term, redox, this is reduction and oxidation. There's also a ton of biochemistry that's tied in with redox chemistry. Again, with the electrons moving, giving us energy and all sorts of things that are imperative for life on Earth. Okay, so I cannot understate the importance of it just because it's everywhere. All right, so we've got this idea of reduction versus oxidation. And as a review with reduction, if you recall, there's a mnemonic device that I've talked about, Leo says grr, where here with oxidation, we are losing electrons. Losing electrons means oxidation. Okay, so this is losing electrons. And GER, G-E-R, gaining electrons is reduction. So this is gaining electrons. All right, so we're always going to have these come in pairs, reduction, oxidation, because the electrons that are lost from oxidation then go over to the species that's gaining electrons, that's being reduced. Okay, so we're always going to have that kind of pathway. And we definitely talked about that when we talked about batteries, because batteries are giving us electricity, a flow of electrons in that way. So, hey, Mickey Happy, nice to see you. That's great. Oh, Neil is so cute. That little emote. Okay. All right, awesome. So that's our little review of redox chemistry. Okay, so to really get to the nitty-gritty and know what's going on with any kind of redox reaction, we must be able to figure out what are the oxidation numbers. Okay, so let's look at what this means and how we figure them out. All right, so like, what is an oxidation number? You just said oxidation is losing electrons. What's an oxidation number? Okay. So oxidation number. So this is a great way to understand what is the mismatch between the number of protons in an atom and how many electrons are there. So if we take sodium as an example, ooh, we get to grab the periodic table, my favorite part of the whole day. Okay, maybe not my whole day, but all right, let me bring this up a little bit so we can find sodium. All right, so we're going to zoom in on this part of the periodic table. It's still really warm here, so I'm like, taking my shoes off. Okay. All right. Hi, everybody. Do you like, I love this is on my face. Neil's in my mouth. Okay. So, sodium. All right, so check it out. Sodium has atomic number, what? 11. This means there are 11 protons. Okay, so sodium, elemental sodium, 11 protons. So that means that elemental sodium has how many electrons? So if sodium is, we're just talking about the neutral atom, and it has 11 protons, so I'm making protons, I'm putting a plus sign since protons are positively charged. Okay, electrons are negatively charged. So the neutral atom has how many electrons? You tell me, how many electrons? Put it in the chat. Neutral sodium has 11 protons. 11 protons, how many electrons? This is a speed test. 11. Yes, this one goes to 11. All right, does anyone get that reference? This one goes to 11. In the meantime, I'm going to put 11 there. Okay, yes, indeed. So 11 protons, 11 neutrons. We're neutral. Great. Okay, so what if sodium loses an electron? What if sodium loses an electron? Because that's what sodium does. So does lithium, hydrogen, lithium, sodium, potassium. All of these group 1 metals, they tend to lose 1 electron. Group 1, we have 1 electron in the outermost shell, it will lose an electron very easily. Okay. I'm still not seeing anyone say what that reference, this one goes to 11, is from. If no one says it, I will tell you. Because it's a must-see movie. Well, it's a must-see movie for some people. If you like mockumentaries, and if you like music, it's so funny. It's so funny. Okay. It's a very good movie. All right, so here we have this neutral atom, but then, as we just acknowledged, sodium group 1 easily loses 1 electron, and so that would mean that sodium, after it's lost its 1 electron, is now positive 1 charged. Okay, how do we know that? Well, sodium, no matter what, if it's sodium, it has 11 protons. The number of protons dictates what element it is. If it has 11 protons, it's sodium. If it's sodium, it has 11 protons. That never changes. Those two things go hand in hand. Okay, so that means we still have those 11 protons for this, sodium plus 1, but it lost 1 electron, and so that means we have 10 electrons now. If this happens, this is oxidation that's happening right here, losing electrons, right? So now if we look at the mismatch here, we have 1 extra positive charge. We have 1 more positive charge than we have negative charges. And so that means that it results in a cation. A cation that has a plus 1 charge, or in other words, oxidation number. There's another term for that, is oxidation state. So don't be surprised if you see that term, or if you hear me say oxidation state, it's the same thing. Oxidation state, oxidation number, charge, all of those are meaning the same thing. That's this mismatch between number of protons and electrons. So that is really helpful to know how to figure out what is the charge or oxidation number of something, because that's going to allow you to figure out what's getting oxidized and what's getting reduced. That is a crucial, fundamental aspect to redox chemistry. Let's do some examples. I think really doing examples is one of the best ways to know how to figure out what are oxidation numbers. Let's go through some of those. If we have atoms in their elemental form, the oxidation number equals 0. Okay, so this is essentially what we just talked about here with sodium. 11 protons, 11 electrons, cancels out, and so oxidation number is 0. And so that would be true for our sodium that we just saw. It is also true for, let's say, a non-metal. So this is a metal. Let's say we have a non-metal like graphite that's just carbon, nothing else. Same with that. And it's also true for diatomics, like O2. So even though there's 2 of them that are bonded together, this is how that atom exists in its elemental form. So oxygen naturally is O2, nitrogen, N2, chlorine, Cl2, you get the idea. So anything that is how it exists naturally, it's going to have an oxidation number of 0. Okay, so that is helpful whenever we're looking at like a big picture of like a chemical reaction, and we can look at it, and a lot of times almost immediately we can know whether it's a redox reaction or not just by knowing this alone. Let's look at, we brought up the periodic table before, and I mentioned something. I want to make sure you remember this. If you recall from previous live streams or classes you've had or anything else. And if you don't know this, then this will be great, as this is going to be really helpful. All right, so group 1. Group 1, all these elements have 1 electron in their outermost shell. And they very easily lose that 1 electron. So as we just said, these tend to become positively charged just +1 because they lose that 1 electron. So it follows that any element in group 1 tends to be +1 oxidation number. Group 2 elements, they have 2 electrons in their outermost shell. They tend to lose 2 electrons and become +2. Same idea. Okay. Then there's a whole bunch of funky stuff that happens in here. All right? And so this region, the transition metals, these are ones we cannot rely on. All right? So we need to rely on other elements in the compound that we do feel confident we know what their oxidation number is. And then we can back calculate and figure out what the oxidation number of these is. Okay? So, for example, iron can be +2, and it can also be +3. Occasionally, but rarely +4. So right there, we can't rely on it unless we know what it's combined with. And so let's go over to the nonmetals, and let's talk about the nonmetals that we can feel, come over this way, that we can feel confident about in terms of knowing what their oxidation numbers are. So, for example, our noble gases, okay? So our noble gases have 8 electrons in their outermost shell. 8 electrons. The octet rule talks about stability of elements when they have 8 electrons. So these being stable with already having 8, that means they're not going to be very reactive, and we will very rarely see them ever combined with anything else. Okay, so then we can check out group 7 right here. Okay, so group 7 is just 1 electron away from having its octet. So these elements will tend to gain 1 electron so that they can have their octet. So group 7 tends to have a charge of -1. And we can count on fluorine. When it's in a compound, it's always going to be -1. These other ones, if they're with a metal, yep, they're going to be -1. When they're combined with nonmetals, it just depends on which nonmetal they're with and all that kind of stuff. Okay, then we can go to oxygen. Oxygen is almost always, for the same reason fluorine is -1, oxygen almost always -2. Because if it gains 2 electrons, it's got its octet. So that one is pretty reliable. A very common exception to that is in hydrogen peroxide, and then oxygen is -1. And that's an unusual thing, but hydrogen peroxide is actually fairly common, so that's one we want to know.